This is Matthew Sherland. I am going over the one-line diagrams for the 243 NEC and NESC project. So this is the NEC part for the installation of 2 new panel boards and a transformer to the OIT campus. Panel board 4A1 is rated at 480 volts and 225 amps, and that ties directly into the utility switchboard at 480 volts and 3000 amps. Panel board 2C2 is only 208 volts and 225, thus it is connected to this Schneider electric transformer, and that has a ratio from 480 volts to 208 volts, and then the 480 side of the transformer is tied to the 480 volt switchboard. Now, using the load schedule, the current coming from this, or the current demand of this 2C2 panel was at over 27 amps, and the current demand of the 4A1 panel was at over 107 amps. Now I multiplied those by 125% to get the conductor rating for those, and on this side of the 2C2 panel, that was going to take AWG10 THHN wire to meet that current demand. Now, using the turns ratio, and that's for a transformer, the reciprocal of a turns ratio is equal to the current ratio. That gives me a current of around 12 amps here between the transformer and the switchboard. For that, I'm using AWG 14 THHN wire to be sufficient for that current. And over here from panel board 4A1, I'm using AWG1 wire. That was the wire that was required in order to meet that kind of current demand. The fuses are rated here on the secondary side of the transformer, which was the current times 125%, and on the primary side it was a current times 250%, and so that is why I'm using a 35 amp fuse and a 30 amp fuse here. And then for the 4A1, I use the 125% formula to calculate the current for this one. This one came out to be over 130, so I just stepped that down to a 125 was the nearest rating fuse for that, which is still over the normal current demand, yet high enough to be tripped in case of overcurrent. Now going over to the NESC project. This was for the installation of 4 new taps to our transmission system to supplement 4 new 20 megawatt solar farms. So the fault current for this system was rated at 1515 amps. Using that current is what we basically switches on, and so we wanted ones that could handle that. The 2 types were D types, which are rated at 1600 amps, and the other type I used was E type, which is rated at 2000 amps. These 2, marked DB, these are bare switches. Bare switches are only rated up to 5 miles, and my distance here was only 2.4 miles. But for some of these other segments, the biggest distance I had was up to 47 miles. And for those, I needed load break switches, which is what all the rest of them are. The load break switches are rated up to 50 miles. For most of the load break switches, I used the D-rated ones at 1600 amps. However, for the 2 that were next to the substations, I used the E-rated ones at 2000 amps. That's because I assumed that the current was going to be greatest right immediately adjacent to each substation, where the sum of the currents coming from the solar farm add together. Have each of the distances marked. Ratings for the entire system are listed here. The system uses ACSR IBIS wire, which is rated up to 1500 amps, and the system operates at 115 kilovolts. That was the general overview of my tube one-line diagrams. Thank you.